So the last talk of the session will be by Umang Mathur, and it's on the complexity of testing message passing concurrency.
Unfortunately could not travel. Together with Lasse and Andreas, who are at the at Aarhus University. And this work stems from our desire to improve the state of the art in program analysis for a language like Go, where message passing communication is a sort of key mode of communication across Go routines. And let me sort of do the routine pitch for why do I care about this problem. Well, because no matter what software application you pick, it's very likely built using concurrency in mind. And in fact, if you talk about modern AI revolution, it would not be an overstatement if I say that it's partly because of concurrency-centric advances in both in hardware and software. But at the same time, we have to acknowledge that developing concurrent software is not an easy task, primarily because if you really go and reason about all interleavings, that's a very large space of interleavings. And for this very reason, many concurrency bugs escape into production level software, and that's not ideal. So one of the popular ways of analyzing programs or concurrent programs so that you can minimize some of these errors is through variants of what I call dynamic analysis or dynamic program analysis. Where essentially you look at one or many executions from your program and then sort of do some sort of lightweight testing based on that. And two of my favorite dynamic program analysis for concurrent software are predictive analysis and model checking. So let me first tell you what predictive analysis is. Here you look at your program and you, with the hope of analyzing an execution, you execute the program. And then perhaps you may not find a bug right away, but you can perhaps try to also reason about possible other interleavings that you can infer from this particular execution. And in doing so, you may be able to find a bug. And this is essentially the essence of predictive analysis. Model checking is also sort of similar in a very broad sense. You have a program and you explore all the executions of the program, let's say up to a bound. And these days, modern model checkers are sort of smart in the sense that they don't really explore every possible interleaving. They allow you to do some optimization, and the most famous one is the deep OR optimization or partial order reduction based optimization, where you only execute one execution per equivalence class. So the black lines are those interleavings. And implicitly, you essentially also get the guarantee for the entire equivalence class, the green region. So why am I talking about these two in particular? I mean, of course, they are my favorite, but also because the core problem that you end up solving when designing such analysis is the consistency problem, and that's what this work is about. So, if you haven't yet gotten a hang of predictive analysis, let me sort of run you through yet another example. So here I have a Go program, and it is a bit problematic because over here I have two Go routines, and they're talking on a common channel, and one of the Go routines has the ability to close the channel. And as such, if you've written many Go programs, you would see that this is not really a nice program, because if you're under some bad interleaving, you may actually end up closing the channel before the other Go routine accesses it. So as a developer, I may be interested in finding these kinds of bugs. And let's say my go-to technique is dynamic analysis, where I draw an execution from the program and look at it. So let's say this is the execution that I got out of it. And here, unfortunately, because my testing is not so thorough, I actually got a very nice execution. It's not buggy. Here, the close of the channel happens way at the end, so it doesn't really expose a problem. But if you pay attention to it, you can actually reason about the problem anyway, because you can say that, well, if I look at this execution, I can actually reorder the send event on thread T2 all the way to the end, and this hypothetical reordering is actually bad because it will raise a panic in my Go program because it's accessing the channel after the channel is closed. Okay, so that's essentially how predictive analysis works. And as I said, the core question that comes up in all such analysis is the consistency question. So if I have to reason about these kinds of interleavings and ask about is there another interleaving, blah, 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 then I have to be very careful because it's not like all permutations of the observed execution are actually going to be valid. There are going to be constraints that one must satisfy so as to ensure that the interleaving that you're thinking about is really an interleaving of the same program that gave you the execution in the beginning. Now, with that in mind, one can actually phrase this as a computational problem. And the computational problem can be sort of very succinctly described as follows. To begin with, you take your execution and you sort of let go of some serialization orders and you retain the very core essence of that execution. I call that a partial execution. It talks about what are the set of events in that execution together with, let's say, what is the order between events of the same thread and other kinds of dependencies that must be respected in all other interleavings. And together with that, you also have to talk about the communication paradigm. In this case, the paradigm is channel-based communication. So the key question that you end up asking is, I'm given this partial execution, and I'm interested in checking if there is a total order of this total order extension of this partial execution, which is also communication safe in the sense that it will indeed be executed by a valid Go program. In fact, the very same program that gave me the very first execution. Okay? So in all these analyses, this is indeed the key computational question that you end up solving. And in this work, we essentially take a thorough complexity theoretic investigation about this problem. So we're looking at the problem of checking channel consistency. I have sort of roughly told you what this is about, and in the coming slides I will go in much more detail because the audience may not have a lot of background over here. And we studied two variants of this problem. One is the channel consistency verification and the channel consistency verification under reads from mapping. So these are the two variants of the question that make much sense in the kinds of applications that one typically looks at in concurrent program analysis. And in this paper, we sort of look at this problem from a computational lens, and we identify how difficult is this problem, and we sort of state some lower bounds on solving this problem. We also come up with upper bounds, which in some sense are actually very optimal. They're matching upper bounds. And we also evaluate our algorithms and test if they really would fare okay in practice. Okay, so with that in mind, let's go through things a little bit slowly. So if you think you may already know this space, it's a good time to go to sleep. I'll wake you up in 5 minutes. Okay, so what is the setup? The setup is you're given a partial execution, so let me first define what that is. So a partial execution is this sort of a tuple. It talks about a set S of events. Events can be one of sends or receive events. So each event is of this kind. It tells you what is the thread that performs that event. So T is the thread over here, together with what is the operation that was performed in that event. See, so operation can be one of send or receive in this case. And there's additional information about the channel identifier, CH, over there. And finally, you also talk about what is the value being sent or received in that channel. So in some sense, this is essentially capturing whatever you really require to talk about to detect bugs. On top of that, in this particular setting, and more in the context of Go, Go has this peculiarity that it allows for channels which may have capacity which is not 0 or not 1, but maybe a finite capacity or sometimes even infinite capacity. And finally, you also talk about what is the program order on this set of events. So this is something that you would have to respect when you're talking about possible interleavings. So this is your input. A slight variant of this input is the reads from setup, where you're additionally also given a reads from mapping. In this case, reads from mapping basically means for every receive event, what is the corresponding send event that it is receiving from? Okay, so that's the kind of inputs to my algorithmic problem. And some terminology over here, if I have a channel, then I call it a synchronous channel if its capacity is 0. So a language like Go allows you to communicate through synchronous channels, where the semantics is that if I decide to send over a synchronous channel, then the receiver must immediately be available. Likewise, channels are asynchronous or non-blocking if you can sort of send multiple messages. You can send one or more messages and sort of move on. And finally, Go also allows you to have channels of unbounded capacity. All right, so that was part of the input. Let's also now talk about what are the kinds of things that we're looking for. So we're looking for an interleaving of those sets of events. So let's talk about interleavings. So an interleaving sigma of n events is a completion of the partial execution that I just talked about. If number one, it's a serialization of the set S. So S is equal to the set even through En. This total order also respects the program order. And finally, it also respects the reads from mapping, if that is also part of your input. By that I mean, if I look at the ith send and if I look at the ith receive, they are indeed those that my input asks for. Okay, so now it's a good time to talk about what is the problem statement. So the problem statement is to check for channel consistency. So you're given a, okay, so maybe let me sort of rephrase it as a consistency condition. So you're given a total order, and the total order satisfies channel consistency if it basically does not, if it continues to obey the FIFO semantics of channels. So that means that if I look at the ith receive, then its value is the same as that of the ith send. That happens for every channel. And because channels may have capacities, you also have to sort of say that if I have a synchronous channel, then every send of that channel is immediately followed by a receive, and you cannot have unmatched sends. And finally, if I have a channel of capacity, let's say 5, then I also require that, at any given point in the total order, if you look at the channel, you cannot have more than, let's say, 5 events. And you have to have it. You have to have more sends than receives. So that's sort of roughly mathematically capturing the intuition of FIFO semantics. All right. So now is a good time to talk about the problem statement, which is that you're given a partial execution, and you have to report if there is a completion of the partial execution that is also channel consistent. And the reads from variant of this problem is, this time you're given a partial execution that also talks about the reads from mapping that you must obey, and you have to report if there is a total order extension of this partial execution which satisfies the channel consistency conditions. Okay. So it took me a long while to get here, but now you can wake up. Okay, so let's now talk about the key results of the paper, and much of the paper is really about complexity in algorithms, so I will also try to focus on those parts. Towards the end, I will also talk a little bit about how the algorithms that we develop also fare in practice. All right, so remember our input is of that kind. Our complexity results are going to be stated in some of the parameters of the input. So the parameters are the number of events n, how many threads you have, T, that turns out to be a very good parameter to talk about, the number of channels, M, and also what is the largest capacity of the channels that you have. So, for the experts over here, it would not be a surprise if I tell you that this problem of consistency checking is actually NP hard. But the interesting part is that it's NP hard in sort of very surprising ways, something that you would not see in the case of registers, where shared memory-based communication. So we actually we show that in each of these cases, the problem continues to be hard. So single value basically means that all channels are communicating only a single value. So even that degenerate case is also very difficult for channels. So on the other end, we have algorithms that are of this kind. They work in time complexity n raised to t multiplied by t raised to km. And if you sort of pay attention to it, it's actually a better algorithm than something that iterates over all permutations, because that would take, I think, something around t raised to n time. So n raised to t is better than t raised to n because the number of threads is typically much smaller than the length of the execution itself. For the dual problem of read-from consistency, unsurprisingly, we also have NP hardness, and this also the interactability continues to hold in pretty degenerate cases as well. And some of these are sort of surprising if you think about the shared memory version of this problem. And on the other end, we have upper bounds, which are slightly better than the harder problem of VCH without the reads from. And then we also look at some other interesting cases which we think do arise in practice. One of them is acyclic topology and the case where every channel is synchronous. So I do have some time, right? Okay. All right. So let me talk about where does the difficulty really come from. The very first observation that I'd like to make is that this problem VCH is actually harder than the corresponding problem when you have registers. And that's because you can actually simulate registers using channels, in fact channels of capacity 1. So roughly the construction goes as follows. You sort of, for every write event, you translate it into a bunch of sends and receive events. It basically says that you have to do many sends, and then you have to do some amount of receives, so that when I see later read events on this channel, I will be able to sort of to dequeue the channels and things work out. So you don't need to worry about it. So the bottom line is that this problem is harder than the case of registers. But what's interesting is that for a much simpler case where the problem is actually very easily solvable for registers, namely when you're given an instance and every value is the same. Imagine if you're given such an instance in the case of registers, you can pretty much in linear time, I mean I would think constant time, determine if that is indeed a consistent instance. The only time it won't be consistent is if there is no write, otherwise it's always consistent. So it's like an order 1 algorithm. But when you have channels, you can do many fancy things. You can basically sort of, you essentially have access to a tape, like a Turing machine. And for that reason, you can actually simulate the Hamiltonian path problem. I don't think I have the time to go through the reduction, but it's pretty cute, so you should go and check out the paper. Let's also talk about the algorithm for VCH. As such, if you've looked at consistency problems before, this algorithm that we have has a very similar flavor to what is generally called as a frontier graph algorithm. And remember, the goal of the algorithm is to come up with a complexity of the kind n raised to t and not t raised to n. So if you think about it, n raised to t you would get because you're trying to enumerate all possible sets of events which are downward closed with respect to program order. And the number of such sets is approximately of the order of n raised to t. So I'll probably very briefly skim through what this algorithm really does. So it essentially constructs a graph on these downward closed sets. Each of the nodes in this graph is called a frontier, and you can think of a frontier as some sort of an abstraction of a partial execution. So each such node talks about how many events have been executed in each thread, and also for every channel, what are the contents of that channel, and extra information around that. So I don't think I have the time to go through the details over here. And on top of that, you can also talk about how I can extend one frontier to a slightly larger frontier using an event, basically by adding an event in that set of the events. And there are conditions on when such an addition is allowed. And the conditions basically says that, you really need to respect how channels behave. And together, we have a graph which is such that if I look at that graph, then every path in that graph by construction is such that it is indeed a consistent total order of my partial execution. And for that reason, and in fact, every consistent total order is also a path in that graph. And for that reason, the VCH problem can indeed be solved in time that is proportional to how much time you would take to construct the graph and to also run reachability on this graph. And that turns out to be something of the order of n raised to t multiplied by t raised to km. Remember, k was the number of channels, k was the largest capacity of a channel, and m was the number of channels. Okay, so I will very briefly skim through what is this other result that we have. It is about communication topologies, and it talks about a subclass of instances where you can actually solve this problem in quadratic time. So you sort of characterize these instances by looking at how threads communicate with each other, and then you come up with the notion of graph on threads. And if that graph turns out to be acyclic, then it turns out that you can solve this problem in quadratic time, thanks to a very nice compositionality lemma, which says that in such a case, you can actually decompose this problem into pairwise threads and solve each of these problems in pretty much linear time. In quadratic time, and therefore in total also you can solve the whole problem in quadratic time. All right, so now let me sort of walk you through the highlights of our evaluation. How did we do the evaluation? So what do we need for our evaluation? We need benchmarks that can give us these instances. The way we go about this is by collecting all the popular Go software and logging executions from using thread sanitizer and extracting these instances out of it. So these would mostly be positive instances, and we do some surgery to also get negative instances. So it turns out that if you compare it against a vanilla algorithm using SMT solving, because you can encode a lot of these constraints as a SMT formula, you are of course going to be much better than something as naive as that, because these executions can typically be millions of events. So yeah, we do very well as compared to SMT solving. But we took a closer look, and we identified that actually we are also not that good. And it turns out that if you do a better heuristic on top of the algorithm, which is called saturation, you can actually do amazing. So at the end, you sort of end up solving all these instances in reasonable time. So I think with that, I'd like to summarize. I've talked about what is the channel consistency problem, and I've talked about our contributions. We sort of primarily look at this problem from a complexity theoretic lens and show that this is a hard problem even for very simple cases. And then we also come up with matching lower bounds, and we demonstrate the matching upper bounds, and we demonstrate the power of these algorithms through pretty much extensive evaluation. So with that, I'd like to end the presentation.
We are basically out of time, but maybe one quick question. If not, maybe we just thank the speaker once again.